This video is basic differentiation, rules, and rates of change. So we saw the previous section showed the limit definition for finding the derivative. Fortunately, some rules were developed for more complicated situations, so we don't have to always use that. So let's see what we have here. The constant rule. If c is any real number, d dx, or the derivative with respect to x, or actually respect to other variables we'll talk about, the derivative of any number essentially is 0. One way to think about this is, suppose you're taking the derivative of f of x, and suppose it's a number. So if f of x equals 6, that would be just a horizontal line, y equals 6. Well, if you look at that horizontal line, anywhere you draw a point, it's going to have a tangent slope that equals 0. So therefore, the derivative slope of the tangent line would always be 0 anywhere on that line. Now the next rule is the power rule. This says that if you're taking the derivative with respect to x of x to the nth power, so keep in mind, actually you'll see the d here in a second, t, but here's the rule. You bring the n down in front, the exponent, and then you subtract 1 from the exponent. So it's not too bad, pretty easy rule. You'll get familiar with this one real quickly. So the derivative with respect to x of x to the 5th, bring the 5 down, subtract 1 from the exponent, we have 5x to the 4th. Now, everything's not always x, so you see, look at this notation, but notice how the variables match here. That's very important. So d dt of t to the 10th power. So you still apply the power rule here, but since the variable's t, we had to take the derivative with respect to t. So you bring down the 10, subtract 1 from the exponent, you get 10 to the t to the 9th. And x to the negative 7, you bring down the negative 7, subtract 1, it's not negative 6. Negative 7 minus 1 is negative 8. I see people make that mistake quite often. Now, on multiple choice tests, these answers might be converted back to positive exponents. On handwritten tests, I don't force people to have to write it back as positive exponents. Some instructors might. Now, if you're checking an answer in a book or something, they probably would rewrite this as negative 7 divided by x to the 8. But personally, I don't care. I just care that it's the right answer. Dropping the x down doesn't make it any more correct. It just puts it in a different form. Now, be careful here. This d dx of 1 over x cubed, you can't take the derivative of a variable in the denominator of a fraction. So the common mistake when people are first learning this is you don't say, well, that's just going to be 1 over 3x squared. You bring the 3 down and change that to 2. That is absolutely incorrect. You have to have the x in the numerator. So you bring the x up, and that just, so 1 over x to the 3rd is the same thing as x to the negative 3. So you bring the negative 3 down, subtract 1 from the exponent, becomes negative 4. So that's the way you handle it with fractions. Okay, with radicals, you'll have to, refresh yourself on this property right here, which is converting radicals back to exponent form. So we see the nth root will be the n will be the denominator and m will be the power. So the nth root of x to the m is the same as x of m over n. So then the cube root of x squared needs to be rewritten as x to the 2/3. And then you bring the 2/3 down, and you subtract 1 from the exponent. 2/3 minus 1 would be negative 1/3. Now, this next problem is not something you would ever have to do on a test. I just kind of want to show you that suppose this problem was worked out using the limit definition. If we wanted to do x to the 10th, and now you can see why you wouldn't want to do this. I let Maple take care of this expansion for me, so I didn't have to do it. So this mess here in blue is if you just take x plus h to the 10th and did a binomial expansion to it. So we're showing now, of course, you'll see, obviously, using the new rule here, the derivative of x to the 10th is going to be 10x to the 9th. But let's see if this, works itself out like it's supposed to. So if you did the limit of f of x plus h minus f of x all over h, so I didn't write all these other terms because you'll see why we don't need them here in a minute. But anyway, so you see it's x to the 10th plus 10x to the 9th h plus blah, 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 all the way down to here. And then minus x to the 10th. Okay, it's very important that any term without an h in it needs to cancel. So the x to the 10th will cancel. And we're left with 10x 9h plus a whole bunch of h's. Now, the reason I didn't write all this out, notice that, okay, so we're going to factor an h out. But notice when you factor an h out here, every term except the 10x to the 9th right here, every other term's still going to have an h in it because they're all squared or higher for h. So you pull an h out, you're still left with an h. And what that means is that so you take the h out and cancel, but as h goes to 0 and you put 0 into all those remaining terms, they're going to get 0, and therefore you're left with 10x to the 9th, which is the correct answer. So needless to say, we don't want to do the derivatives the long way for those kind of problems, but I just want to show you that. Okay, so there's just an x to the negative 4th. Use the power rule, and I just wrote or that. All right, that's simple enough. Now over here, x to the 1/3. Now take the derivative. That's 1/3 x to the negative 2/3. Now I just dropped these down just to show you. Like I said, if you're taking a multiple choice test, the answers might be written with positive exponents. Handwritten test, you wouldn't have to do that. But I want to show you that if you drop this down, notice if you put 0 into this derivative, the derivative would be undefined, right? Well, okay, graphically, I want to show you the reason why it's undefined is because the graph is continuous. The cube root of x is continuous for all x. But the way it's undefined is from a previous video section, talked about that has a vertical tangent. So the vertical tangent's causing that to be undefined at 0, the derivative, even though the function is still defined at 0. Now notice for this that d dx of just x would actually equal 1. If you wrote it as x to the 1 and you brought the 1 down, and then that would leave x to the 0, which x to the 0 would be 1, assuming that x wasn't 0 itself, but you end up with 1. So the derivative of just x to the first power would be 1. Now here comes some more rules. Constant multiple rule says that if you have a constant multiplied times your function, the constant just stays there. Now, we've already just saw a few minutes ago that the derivative of a constant by itself with no variable is 0. But if it's multiplied by your function, it stays multiplied to the derivative. That's all that's saying. And then, like for example, then if the derivative of x is 1, the derivative of cx would just be c. So like right here, see, it's 5x to the 4th, so the 5 stays there. You take the derivative of x to the 4th, it becomes 4x cubed. Multiply the 5 and the 4 together, and you get 20x cubed. Okay, that's all it's saying. So here the derivative of 7x would just be 7. The derivative of x is 1, but the 7 would stay there, so 7 times 1 is 7. Okay, well here I just went to variable t again just to show you, so I have to rewrite that. T to the 4th root of t cubed is t to the 3/4. Bring down the 3/4, subtract 1. 3/4 minus 1 is negative 1/4, but then 8 times 3/4 would be 6. And right here we have 3 over x to the 7th, as we saw a few minutes ago. You can't, well, there's going to be a rule for division in the next section, but even with that rule, you wouldn't want to use it. What I'm about to do here is much easier than using the rule. But so you bring up the x to the 7th, make it negative 7. So you basically take negative 7 times 3 makes negative 21. Subtract 1 from the exponent makes negative 8. And then that's correct where I have the flag, but then also you could rewrite it with the positive exponent, which is also correct. And here's one where it's just this. I guess this problem could have actually gone a little bit earlier before those properties, but that's okay. Still a valid derivative. X to the 1/4, because that's x to the 1 inside the radical. 1/4 x to the negative 3/4. And then I'm just showing a couple of alternative ways to write that same answer. Sum and difference rules. If you have several functions that are being, and it's more than just two, added and subtracted together, that means you can just take their derivatives individually. And like this one, 3 f of x equals 3x to the 5th minus 6x cubed plus 11. So notice, my derivative notation that I talked about before, you got to use that notation. So in this case, I used f prime of x. So we have 5 times 3, bring down is 15. 5 minus 1 makes 4. This one, you bring the 3 down. 3 times negative 6 is negative 18. Subtract 1 from the exponent, makes it x squared. Now, this 11 at the end, it's by itself. There's no variable. So the derivative of any number without a variable is 0. Of course, mathematically, you could write plus a 0. It would look silly, but you don't need to put the 0 there. So same thing with the next one. 3 times 2 is 6. Subtract 1 from the exponent, makes it x squared. So yeah, so that's this 6x squared is not the 6x squared in the original problem. It's the derivative of 2x cubed. And then the derivative of 6x squared, 2 times 6 is 12. Subtract 1 from the exponent, makes it x to the 1st. And then the derivative of negative 1 would be 0. Now here's something I just kind of want to show you here real quick. I'm not likely to ask this on a test, but if somebody's using this video and needs to use it for their own purposes, thought I would show you real quick. But I'm talking about comparing the graph of a function with a graph of its derivative. And this can be kind of a tricky concept. So if it's a little confusing, that's all right. Unless you don't worry too much about it, unless you have to understand it. In my class, not so much, but I think it's interesting, so I would like to explain it. So I put these two functions in the graphing calculator. That's the derivative, 2x squared would be 4x minus 5x would be minus 5. 6 would be 0. So the parabola is the original function. The line is the derivative. Now, what this is, I've said down here that since the derivative function represents the slope of the tangent line of the original function of the graph, that means anywhere you draw a point on the blue graph and try to want to know what its value of the tangent line is, it would be whatever the y value is on the derivative graph. So for example, like I said, this is kind of hard. I'm going to try to, I want to zoom in, not out. And so I'm kind of freehanding these here without using a stylus, so they're not going to be all that great here. Well, let's take this point. Let's shrink that down a little bit. Yeah, that'll help. Oh, let's make it a different color. How about green? So let's say right here, and I wanted to know what that tangent line value was right there. Now, okay, but you see, so I'm drawing this at x equals 0. That's the key, is the look of the graph and what your x is. X is 0. Now, one thing you can tell about my sorry looking sketch there is we know for sure the slope is negative. That's heading down a negative. But the actual slope then would be if you came down and looked at what the y value is on the red graph, the derivative graph. You don't draw a tangent line or anything on the derivative graph. You just look at what is the y value. The y value is, I should thicken this up again, right there. It's -5. So the slope of that green line is -5 because it's the, in fact, look at this. It's the y value of the derivative. Look at this one right here. That's hard to tell what the x is, but anyway, it'd be easy to visualize. At this point, I'm going to have to shrink that down. At this point right here, you can see that that's a horizontal tangent line. It's going to have a slope of 0. So if I take that point and look at it, whatever it is, 1 point something, I can't tell what it is, but if I come down here, you see on the y-axis, the red graph has a y-coordinate of 0, therefore it's the slope of the graph at 0 for the other one. So you come over here, okay, I'll quit doing this now, but so these are all positive, so if you draw, so much you can kind of just draw a line. So this, let's say right here, that's no good. That slope will be whatever this y coordinate is. Man, it's hard to draw. I'm trying to draw this at x equals 3. So that's that thick green line, that tangent line at 3 on the blue. The slope of that tangent line will be whatever the y coordinate is on the red. So I'll come over here and what is that? 1, 2, 3, 4, 5, 6, 7. It's 7. Okay, so that's how derivatives then relate to their graphs. So, all right. All right, so let's zoom back out, scroll down here. Of course, that was from a visual standpoint. If you didn't have the equation, obviously, if you had the equation, if I plug 3 in there, you would be able to calculate that it was 7 for sure. You know, the one I just drew. So. All right, the derivative of sine and cosine. Now we're getting some trig functions in there to make some excitement here. All right, the derivative of sine of x is actually cosine of x. The derivative of cosine of x is negative sine of x. Ah, very interesting. Negative sine of x. I remember someone asking me one time, did somebody just decide to make that negative to kind of mix it up a little bit, you know, and add some excitement or something? And then, no, that's not generally done in math. You don't do things to create excitement. So it's negative sine of x because it has to be negative sine of x. So I did find that amusing. Well, I think the book shows the derivative of the proof of sine of x equal cosine of x. Now, I don't ever ask this on a test or anything, but I'm going to kind of go through this pretty quickly. If I was going to make you have to do any of this, then, you know, obviously I would be real careful, but you're not. And that's okay if you don't remember this identity. You can find it off any trig sheet. But one thing that you should know, even if you don't remember the sum of, I forget these sometimes too, but the cosine of x plus h, it's okay if you don't remember what it is. Just make sure you realize it's not this, what Stewie says there. Stewie says no. As long as you know it's not this, you're in good shape. And there's what it is actually right here. So cos of x plus h has an expansion, sum expansion that goes cos x, cos h, minus sine x, sine h. So I'm using the limit definition to try to derive the derivative of this. And I needed to rearrange these terms. I brought the cos x over here, and then I brought the sine x over. I flip-flop those, and then property of limit says I can then make a subtraction and separate them completely, which I want to do. And I'm going to be using these two rules we've learned in a previous video before. Those two limits, that's going to come in handy here. So after I split those up, I come down here and I factor out a limit as h goes to 0 cosine of x. And then you're left with cosine of h minus 1, because you factor out a cosine there, you're going to be left with a 1 all over h. And this side, I've split these up into the limit as h goes to 0 of sine of h over h right here, and then just sine of x by itself. So for this one, even though it's h instead of x, different letter, but the same rule applies. If you look at this rule right there, that's going to go to 0. The limit as h goes to 0, keep in mind that's cosine of x, so you don't plug in h into the x variable, so you leave it alone. The limit as h goes to 0 of cosine of x would just be cosine of x. Now you come over here and use this rule. That limit's going to be 1. And then the same thing I said about cosine, the limit of sine of x as h goes to 0 will just be sine of x. Now this 0 will wipe out the cosine of x. So basically you have 0 minus sine of x. And then there you have negative sine of x. Ta-da, there it is. So it definitely is negative sine of x. Now I sketched the cosine graph and the negative sine graph, and if you want to look at that whole slope business here, you can. But I don't want to, go through too much of that, but I'll show you one of them real quick, and then I'll move on. Let's say the blue here, which is cosine, that point right there when it's 0. It has you see the tangent slope would be flat, so the slope would be 0, which is what the y coordinate is of that, or the red graph is 0. So, okay, so I don't want to go back through all that again, but so if you'd like to look around that, play around with that, it might be fun. All right, looks like Stewie's back in this problem. Okay, pi is a number, so it's just a coefficient. So the derivative of pi cosine of t, so the derivative of cosine of t would be negative sine of t. Now, I guess on a multiple choice exam this wouldn't matter, but on a handwritten exam I always, express to students that, I probably would take a point off if you wrote the answer like I have there in green. You need to either use parentheses to indicate that's multiplication, or even better, just take the negative all the way out in front, and you don't have to use parentheses at all then. So because Stewie says the answer in green looks like subtraction, so if you were doing this handwriting the answer, how would I know that whether or not you knew it was multiplied, or how do I know that you might think, I don't know, pi minus sine of t? I have no way to know that you know what the correct answer is. Let's come down here. 5 over 2x cubed plus 2 cosine of x. Now you square this, so you cube out this 2 of x, gives you 8x cubed. And then, but you don't, lots of people make the mistake, I talked about earlier, only the variable part needs to be moved up for derivative purposes. Leave that 8 on the bottom. The 8 doesn't come up with it, just the x cubed. So you leave the 8 on bottom, bring the x cubed up, and then now we take the derivative. So you take negative 3, bring it down, and multiply it by 5/8. So you get negative 15 over 8. Subtract 1 gives you x to the negative 4. And then the derivative of 2 cosine of x would be negative 2 sine of x. Okay, so watch out for that. Don't bring the 8 up. This one's saying 3 divided by the 5th root of x squared minus 7 sine of x plus 2 divided by x over 7. So I need to bring that x to the 2/5 from the bottom up, makes it x to the negative 2/5. Same thing with x to the 7, bring that up, make it negative, and use the power rule for outside terms. Bring in negative 2/5 times 3 is negative 6/5. Subtract 1, you'll get negative 7 over 5. Now, the derivative of sine is cosine. The only reason there's a negative there is because there was a negative coefficient in front. So you see, so it's like, that's why it's negative, but the derivative of positive sine is positive cosine, but the negative 7 just stays there. Now you take negative 7 times 2 makes negative 14. Subtract 1 makes that negative 8. Now this is kind of an interesting little problem here, just to kind of get used when you're talking about taking the derivative with respect to a certain variable. When you're taking the derivative with respect to a variable, that means any other variable is behaving as if it was a constant, meaning it's acting like it was a number or something like that. So I took this same function, a squared sine of t, and then I said, okay, let's take the derivative. F prime of t means you're taking the derivative of this function with respect to t. That means t is your variable and a is a constant. So that means the a squared would sit there. You take the derivative of sine of t makes cosine of t. Over here, if you're defining this function as f of a equals a squared sine of t, and you're taking the derivative with respect to a, that means sine of t just sits there. It's behaving as if it was a constant. And you only take the derivative of the a squared, which makes it 2a sine of t. I thought that was kind of interesting. Always have to pay attention, especially if you see more than one variable there, what you're taking the derivative with respect to. So this one says, now, one of the things we do with the derivative, you're finding the slope of a graph at a single point. That's the whole business about the tangent line and all that kind of stuff. Finding the slope between 2 points, that's just algebra. But finding the slope of the graph at a point is calculus, it's the derivative. So what this question is basically asking is, it's just saying the same thing as find y prime at x equals 1. You're always evaluating the x. So we take the derivative, would be 2 times 4 is 8, subtract 1 is 3. The derivative of minus 3 would be 0, so it's just 8x cubed. And you put 1 in there and you get 8. So what I did was I just graphed, unnecessary to graph this. I graphed it and just kind of drew a rough sketch of what the tangent line would be. Well, I can't necessarily tell that the slope is 8, but I can darn sure see it's a positive slope, so at least in the right sign of it anyway. So, but that was unnecessary to do that. Now we have this function. We want to find the derivative. There will be a rule for division in the next section, but we're not going to need that rule right now. We're going to do this strictly by just taking all the terms on the top and creating them as individual terms by dividing on the bottom. So all we're doing is taking everything and dividing by x, like this. So 4x cubed over x gives you 4x squared. 2x over x gives you 2. 5 over x is the same thing as saying 5x to the negative 1. So I just brought the x up for that one. And let's see what that does for us. The derivative of 4x squared, 2 times 4 is 8, makes it first power is 8x. And then negative 1 times 5 is negative 5. Subtract 1 makes it negative 2. And then over here, I'm just writing the answer 2 different ways. That's all that is. That's not different work. So I dropped the x squared on the bottom like this. And then I said, oh, okay, what if you wanted to bring it back into one fraction? You could get a common denominator by going x squared over x squared. Can't imagine you'll ever have to actually do that. But you just have to look for this kind of stuff if you're trying to choose the right answer, like on a quiz question with multiple choice. Maybe it would do something like that. So that's the only reason. Handwritten, I would never expect anyone to do that. Where it has the UH seal of approval is good enough for me there. So, or the flag or any kind of little thing I put there. The next one, we'll have a rule for multiplication in the next section. But even then, I would not use it here, because I would just distribute the x squared. Super easy to do that. You get 2x to the fourth minus 3x cubed, and that's easy to take the derivative. It'll just be 8x to the third. 3 times 3 is 9, 9x squared. So that's easy. Now we're going to find the equation of the tangent line at the given point in slope-intercept form. I prefer to, well, if you want to use point slope form, you can, but the final answers are going to be in slope intercept form, so you might as well just do it that way. This kind of goes back to something I showed you in the last video. Let me bring this up. I didn't show you how to do this at the time, but now we're about to learn how to do this. That was right here where I typed in this equation without showing how to get it. Now you're going to learn how to get it. So, okay, to find the equation of any kind of line, you need a slope and a point. You can also do it with 2 points, but in this case, slope and a point is what we want. Slope is coming from the derivative. Tangent line slope is the derivative. So the derivative of x cubed minus 3x would just be 3x squared minus 3. So I put in the 2 in there, and you get 9. So the slope of the tangent line will for sure be 9. And as I said in the previous video, that they only have to give you the x here. They don't have to give you the y. You could actually calculate the y. You put the 2 in for x here. 2 cubed minus 3 times 2 will give you 2 for the y. They'll only have to give you the x. So that's why I'm kind of drawing an arrow here to show you that there are two 2's there, but the number we're plugging in is definitely the x and not the y. So that means if I know the slope is 9, my equation is going to start out y equals 9x plus b. I just have to figure out what b is. So to do that is take your xy point. So even if at this time, if you had not been given the y, you would be calculating the y to get it if you didn't already have it. We already have it. So I put in 2 for x right here. I put in 2 for y over here and solve for b. So doing that, you'll get b equals negative 16. And then that means the final answer for the slope of the tangent line will be y equals 9x minus 16. So that's exactly what I would have done in that problem from the last section to come up with that particular line. Now suppose I want to know what the equation of the line that's perpendicular to that tangent line at that point. Okay, this brings back something from algebra days there. Stewie's here to remind you that the product of two perpendicular slopes is -1, meaning also you may remember it as saying the negative reciprocal. One of them is the negative reciprocal of the other. So you don't have to do the derivative or redo any of that process. All you have to do is start with the fact that we know the tangent line slope is 9. Therefore, the perpendicular slope of the normal line will be -1 over 9 because it's negative reciprocal. Then we take that information and we go to y equals mx plus b. So then you just take now you have a new slope and you just put in the x and the y, put in the 2, put in the 2, and you get 20 over 9. And that's your new b. So this equation of the normal line would be -1/9 x plus 20 over 9. And I just graphed all this just for grins. See, there's the point of interest right there. So you can see the tangent line's the red one, 9x minus 16. Yeah, it's running right along there next to it like a tangent line's supposed to do. And then the black line is the third one, and it's looks pretty perpendicular to it. So that looks pretty good. So I feel pretty confident about our answer. Graphing that was not mandatory, but let's look at what this question is asking. Let's say it's saying find the values of x where the graph has a horizontal tangent line, if any. There may not be any. Now you don't need the graph to actually solve this problem, but while this picture's up here, I'm just going to go ahead and show you that you're looking for basically this and that. The values for x where it has a horizontal tangent line. So this graph would have those two answers. So the idea is you take, anyway, horizontal tangent lines are always going to have a slope of 0. Therefore, you take the derivative and you find all values of x that would produce it to produce 0. So you don't plug 0 into the derivative, you set the derivative equal to 0. So here's the function, and you take the derivative of it, so f prime of x will be x squared plus 6x plus 8. Pretty easy. Set this equal to 0. This one factors nice and easy. X plus 4, x plus 2. So the two values then would be -2 and -4. I didn't have to write those in order. Only time they have to be in order is if they're an interval. I guess I could have, but it doesn't matter. Because that's just set notation. That just means those are individual answers. It's not expressed as a range of answers. So that's quite all right. Now suppose instead of just identifying what the x values are of the horizontal tangent line, suppose we wanted to identify what the actual point is, the actual coordinate. No trouble, you could just take your calculator and you would have to put, plug in the x for -2 into the original function, not the derivative. Of course, the derivative tells you something completely different. F of x gives you y. Put in -2, and you end up with -35 over 3. And you put in -4, and you get -31 over 3. So those are the actual point coordinates. You see the y values are kind of close to each other. And there's -2, there's -4, and then you see the horizontal tangent lines. All right, let's try a trig one here. So notice the interval is very important here. I like to keep these on intervals like where they're not, forever and ever, where you don't have to use all that. Like in trig, you might have learned where you solve equations and you have to put the 2k pi at the end of it, or the 2n pi, or anything like that. I'm not interested in doing that. I like to keep it between 0 and 2 pi, or possibly some other interval, but not where it's just going on and on forever. So anyway, the derivative of this function, y prime, would be the square root of 3 times x, would just be the square root of 3. And then the derivative of +2 cosine of x would be -2 sine of x. Now notice this interval includes 0 but not 2 pi, because they are coterminal to each other, so 2 pi would not be an answer, but 0 could be. So I want to set this horizontal tangent line. I want to set this equal to 0. And so you have basically 2 sine of x equals square root of 3. Sine of x is square root of 3 over 2. And then you see on our trusty unit circle, there's the two values where sine would be positive square root of 3 over 2. And they are at pi over 3 and 2 pi over 3. I graphed the function, but completely unnecessary for this problem. But if you want to play around with that, you can. But we found the two values of pi over 3, 2 pi over 3. I mean, there could have been more or less, or none, actually. Like this example. Y equals x cubed plus 1, and x cubed plus x, excuse me. Y equals x cubed plus x, and then the derivative y prime would be 3x squared plus 1. You set this equal to 0, you get x squared equals -1/3. And, well, we're only dealing with real numbers in this class, not imaginary, so that means there'd be none. I thought I had a graph of this one, but I guess I do not. That's okay. It's not a very complicated looking graph, but it kind of looks something like that, sort of like that. Now, x cubed by itself actually flattens out. X cubed actually does this, and then you have a horizontal tangent at 0. But that x cubed plus x shapes the graph in such a way that nowhere on this graph would you be able to draw a horizontal tangent line. So it's correct. You can check it if you wanted to. But now, a horizontal tangent line automatically implies that slope equals 0. But suppose that you had a problem that wanted to know a specific numerical value. So obviously, if it's some other slope value, it has to tell you. Horizontal automatically means 0. So let's say, suppose that we want to find the values of x where the point on the graph has a slope of 3, if any. So once again, we're doing the same process. We're taking the derivative, but instead of setting the derivative equal to 0, we're setting the derivative equal to 3. So the derivative of x cubed minus 6 would be 3x squared. Set that equal to 3. X squared equals 1. Be real careful with this, especially as you go through this class, that when you have x squared equals a positive number, there are two answers there. I've seen that kind of hurt a lot of people before on problems. They forget that plus and minus. So two answers, plus and minus 1. Now I said suppose we wanted to come up with the equation of the tangent line for both those problems. Well, we know the x's are plus and minus 1, so I started with negative 1, so I had to plug negative 1 back into the original function up here to get the y value. So negative 1 cubed minus 6 is negative 7. And we know the slope is 3, because the problem tells us it's 3. So both equations are both going to start out with y equals 3x. They're just going to have different y-intercepts, different values for b, to prevent them from being the same line. So we have 3x plus b. So now we know that when x is negative 1, y is 7. So I put in negative 1 for x, negative 7 for y, solve that simple equation. You'll get b equals negative 4. So therefore, that line will be y equals 3x minus 4. Now for this one, when you put 1 in there, you'll get negative 5. 1 cubed minus 6 is negative 5. So I have y equals 3x plus b again. Put in 1, put in negative 5, I'll get negative 8 for b. So my other line will be 3x minus y equals 3x minus 8. Now let's look at this. So I graph the original. Oh, that's not what I wanted. So the values are plus and minus 1. So there's negative 1. There's positive 1. So you see those tangent slope, they're both parallel. Those lines are parallel because they have the same slope of 3. So you see there, so at negative 1 and positive 1, you have those parallel tangent slopes. So those are the values for x that will guarantee they will equal the slope of 3. Now I mentioned in this paragraph that this problem could have also been worded like this. You know, it could have said, find the values of x where the slope is parallel, using the same function, of course. You have to have the x cubed minus 6 or whatever the problem is. So what if it would have said, instead of saying where the slope equals 3, what if it would have said parallel to the line y equals 3x plus 10? Well, if it's parallel, it's going to have the same slope. So that's really just an equivalent way of saying that the slope is 3 by wording it that way. Same thing. So the process would be exactly the same. Rates of change. So let's talk about that for a bit here. Now, we've talked in previous sections about what slope of a secant line. That's slope of a line between 2 points, but that also measures the average rate of change. So it means what's the average rate of change over a function from 2 points in time. Also, average velocity, if you're talking about a velocity problem, be your average velocity over a period of time. So, so let's say if you were, let me see if I have an example of that. If not, I'll say, well, okay, I'll just say this verbally then. So let's say that you're traveling, and then, after 1 hour, you've traveled 60 miles, and then after 5 hours, you've traveled 320 miles. You could then calculate what your average rate would have been for that from hour 1 to hour 5. You would just take the 320 minus the 60, divided by 5 minus 1. That would let you know what you averaged at through that time period. So that's what average rate of change is. What you're averaging, basically the slope of a secant line over a certain period of time. Now, slope of the tangent line, which is the derivative, that measures what's called the instantaneous rate of change. In physics, once again, the most commonly used thing for that would be instantaneous velocity. Now, if you're driving an automobile, that's an easy thing to figure out. If you just look down at your speedometer, you see at any point in time, you know what speed you're going. Well, let's say we have some sort of path of some particle that's modeled by some equation. We could figure out at what speed it was traveling at any single point in time by the derivative of the function and then plugging in that value, that time value. Let's take a look down here. So this says find the average rate of change on this interval of sine of x, and then find the instantaneous rate of change at each endpoint. So it's 0 and a pi over 6. All right, average rate of change is slope. y2 minus y1 over x2 minus x1. So it's f of pi over 6 minus f of 0 over pi over 6 minus 0. Sine of pi over 6 happens to equal 1/2. Sine of 0 is 0. Pi over 6 minus 0 is pi over 6. So 1/2 divided by pi over 6, flip it over. So the exact answer, which I like to get exact answers whenever possible over decimals, is 3 over pi. So you could, for your own edification, you could calculate 3 divided by pi, but that's good enough right there. So that's what it's averaging in that time period. So let's see what it's doing at the endpoints. The endpoint would be instantaneous velocities at each endpoint. So you have to take the derivative of your function, sine of x. The derivative of sine is cosine. You plug in 0, so that there would be 1. And then plug in pi over 6, it would be the square root of 3 over 2. So that's the specific velocity at those points in time. But it's averaging 3 over pi throughout the entire. So it's a little bit faster at 0, because 1's a little bit bigger than 3 over pi, but square root of 3 over 2 would be smaller than 3 over pi. So it's kind of slowing down there. It's not traveling as fast at pi over 6. And those speeds can vary throughout the interval. All right, here's a function that's f of t equals t cubed minus 7. Find the average rate of change on the interval at each endpoint, and also t equals 4. I went ahead and chose a t value in the interval. So the average rate of change, f of 5 minus f of 3 over 5 minus 3. Plug in 5 cubed minus 7 is 118. Plug in 3 cubed minus 7 is 20. So it's 5 minus 3 is 2, 118 minus 20 over 2 is 98 over 2, which is 49. There's no units involved. I mean, if there's units involved, we'll see that here shortly, but don't worry too much about that. In a handwritten exam, I don't worry about units that much. And if it's multiple choice, it may not give the units. If it does, don't worry about it. But I would not use that strategy in a physics or engineering class. Units are extremely important. Alrighty, instantaneous velocity would be, or rate of change, I should say, it's not necessarily a velocity. Instantaneous rate of change would be the derivative of t cubed minus 7, which f prime of t would equal 3t squared. So at 3 and 5, at 3 it's 27, 3 times 3 cubed. At 5, squared, which is 3 cubed. 3 times 5 squared is 75, then f prime of 4 is 48. So it's kind of picking up speed along the interval if you're measuring it that way, velocity, it's picking up velocity. But anyway, with that being said, it's the average throughout the entire interval is 49. You can't just average the endpoint values and come up with that answer. In fact, you see, if you add up 27 and 75, that's 102 divided by 2 is 51. But theoretically, it's the average of all real numbers throughout the interval, not just. All right. No, actually, it's just the average of the endpoints, I should say. I'm going to correct myself there. But anyway, with that being said, position function of a falling object. This is a nice little physics exercise. You don't have to memorize this equation. I probably would give this to you with a g already in there. So g is acceleration due to gravity, which is constant depending on what units you're using. Negative 32 feet per second squared. If it's English units, negative 9.8 roughly. I think negative 9.81 or something, but meters per second squared. V0's initial velocity. S0 is your initial height. So the initial velocity would be if you were actually throwing an object down versus just dropping it. If you're dropping it, that v0 would be 0, but if you're kind of helping it along, it would have an initial velocity. If you take this function, the velocity function of a falling object, which is your instantaneous velocity, would just be the derivative of that position function. So the derivative of 1/2 gt squared, take respect to t squared, 2 times 1/2 would cancel, so it leaves gt, and the derivative of v0t would just be v0 because the derivative of t is 1. So that's without any numbers in there. That's what the instantaneous velocity equation would look like. All right, let's try this problem out. Now, of course, we are operating under the assumption here that we are not dealing with any kind of wind resistance, perfect vacuum, so to speak, I guess. So we'll just kind of go with that assumption. Essentially meaning that if you drop a coin or drop a feather or whatever, it's not affected by anything else. So, all right. So 1,362 feet tall. So it's an English unit, so the gravity would be negative 32 feet per second squared. Now notice it says drop, so drop means the initial velocity would be 0. So with part A, we're identifying what the position function is and the velocity function. So 1/2 gt squared, so half of negative 32 would be negative 16. So it'd be negative 16 squared, and there's no v0 in this problem because we're dropping it. And the initial height, s0, would be 1,362. So that's our position function. So that means you can plug in a value for t. Now, and then that will tell you how high it is at any point in time until you reach the point where it's hit the ground. So any number for t larger than that would be not applicable, because if you plug this in there and you get some sort of negative height, that means you've put in a value for t that's too large. And so the velocity function, the instantaneous velocity, would be the derivative, which is negative 32t. So this question is asking what's the average velocity on the interval from 1 to 2. Okay, that average velocity means that's not a derivative. That's not calculus. You just basically take the position function s of 2 minus s of 1 over 2 minus 1. So we do not use the v of t. So you plug the 2 in here, this function, you'll get 1298. Plug in 1, you'll get 1346. So you work all that out, and you get negative 48 feet per second. Now, the negative just means that velocity involves direction. See, speed doesn't involve direction. Speed is always positive, but just the negative means because it's heading downward at 48 feet per second. Alrighty. Now, what are the instantaneous velocities at t equals 1 and t equals 2? Now, this will be the derivative. So we will put in 1 in the negative 32t is negative 32 feet per second. When you put in 2 is negative 64 feet per second. Negative 32 times 2. Now, in this case, the average velocity, because it's a parabola equation for this kind of problem, would be the average of the instantaneous velocities. That's only true in this case. The example I did a few minutes ago up here, it was not true. But it's only true in this particular problem because of the quadratic. But this t cubed problem I did, that was not true. You see the f prime of 3, f prime of 5, I talked about the average velocity was not the same. But yes, it would be for the falling object problem. It would be the same. It would be the average of those two numbers. Find the time it takes to reach the ground level. So that's just a matter, your s of t is your height. So you just replace that variable with 0, and then you just solve that for t. This could get a little messy, I guess, if you had initial velocity, because you'd have a t variable there. But you could always use the trusty quadratic formula, or you could even graph it if you wanted to and look for the intercept. But this one's no trouble because it's no t there, so you can just move the number over to the other side and solve it that way. If it was another t there, you'd have to use a quadratic equation, but move this over. Now, I wrote plus here because mathematically the solution to this equation, always important to remind you of that, is that when it's a squared variable, technically it has plus and minus, but in this application you would not have a concept of negative time. So we would only use the positive number even though mathematically there are two numbers. So it would be the positive square root of 1362 over 16. So it's going to take roughly about 9.226 seconds for that thing to hit the ground. So what's the velocity at impact as it's hitting the ground? So the velocity is negative 32t, put in 9.226, and it's traveling at negative 295.2 feet per second. So you see these velocities. So basically the moral of the story, if you were going to get hit by this silver dollar coin, it would be much less damaging to get hit early on when it's not traveling as fast. You do not want to get hit by this thing while it's traveling down to the bottom, because it might just turn your head into a human piggy bank if it hits it just right. But if you stuck your head out the window of the building early on, hit you, maybe it wouldn't hurt so bad, but bad news at the end. And that concludes this video.